Good evening, everybody. Today we are going to discuss about applications of Laplace transforms. Fourth unit. Fourth unit is applications of Laplace transform and resonance. Coming to definition of Laplace transform. Here, f of t. This is f of s. Okay. F of t. This is in time domain. Okay. A time domain function. This is time domain function. Time domain function. F of s. F of s. This is in frequency domain. This is frequency domain function. Frequency domain function. Frequency domain function or S domain or S domain. S domain. S domain. Okay. In order to convert from time domain to frequency domain, we use Laplace. Okay. F of t. Laplace transform is a tool which is used to convert time domain into frequency domain. F of t into f of s. Okay. By using Laplace transform. Okay. So this is in time domain, whereas this function is frequency domain function or S domain function. Okay. So Laplace of f of t. Laplace of f of t is equal to f of s. Use Laplace transform tool to convert time domain into frequency domain or time domain into S domain. Okay, this is time domain function, whereas this is S domain function or frequency domain function. Okay, here we have the definition. By definition, we have this formula. F of s is equal to integration from minus infinity to infinity f of t e power minus s t dt. Okay, this is two-sided Laplace transform. This is two-sided Laplace transform. Okay, defined from minus infinity to infinity. Two-sided Laplace transform. Okay, two-sided Laplace transform. Okay, coming to this formula, f of s is equal to integration from minus infinity to infinity power minus s t f of t u of t dt. Here u of t is included. U of t is included. Okay, what is u of t? U of t is unit step function. U of t is unit step function. Okay, this is u of t waveform. Okay, this magnitude is equal to 1. This magnitude is equal to 1. Okay, unit step function means here u of t is equal to 0 for t less than 0. For t less than 0, u of t is equal to 0, whereas u of t is equal to 1 for t greater than 0. T greater than 0. Okay, so for t less than 0, this value is 0. U of t is 0. For t greater than 0, u of t is equal to 1. Okay, this is unit step function. Unit step function. Okay, here when you include this u of t here, okay, actually the function is f of t u of t. You are converting this function into S domain. Okay, so f of t u of t means this function is defined only for positive values of time. Okay, for negative values of time, this value will be 0. That value will be 0. Okay, so you're going to get one-sided Laplace transform. You're going to get one-sided Laplace transform because other side the value would be 0. The value would be 0 because u of t will be 0. U of t will be 0 for t less than 0. So this is one-sided. This is one-sided. One-sided. One-sided Laplace transform. One-sided Laplace transform. Okay, one-sided Laplace transform. Right. Okay, so one-sided means integration from 0 to infinity e power minus st f of t dt. F of t dt. Okay, this is what one-sided Laplace transform. But here instead of putting lower limit 0, let me include, let me have lower limit 0 minus. Instead of having 0 as lower limit, let me have 0 minus as lower limit. 0 minus as lower limit. Okay. See, if there is any discontinuity at t is equal to 0, I must include that discontinuity. Okay. So in order to include that discontinuity at t is equal to 0, I should consider 0 minus as lower limit. I should take 0 minus as lower limit instead of 0. Okay. So after after considering 0 minus as lower limit, we are going to have the formula like this. Laplace transform of f of t is equal to f of s. Laplace transform of f of t is equal to f of s, which is equal to integration from 0 minus to infinity f of t e power minus st dt. Okay, so this is what? This is one-sided Laplace transform. So Laplace of f of t is equal to f of s, which is equal to integration from 0 minus to infinity f of t e power minus st dt. Right. Okay. Now coming to unit step function. Okay. For t less than 0, the value is 0. For t less than 0, so here u of t is equal to 0. 0 for t less than 0. For t less than 0, which is equal to 1 for t greater than 0. If t is equal to, it jumps from 0 to 1. It jumps from 0 to 1. Okay. So this is only defined for positive values of time. This is only defined for positive values of time. Okay. So Laplace of u of t is equal to any of, even if you take integration from minus infinity to infinity. Okay. From minus infinity to 0, u of t will be 0. U of t will be 0. Okay, so that's why you take limits from 0 minus to infinity, as this function is defined only for positive values of time. As this function is defined only for positive values of time, you take integration from 0 minus to infinity. Okay, and then Laplace of u of t is equal to integration from 0 minus to infinity e power minus st f of t, right? Here f of t is u of t, because you are going to find Laplace of u of t. So in place of f of t, you write u of t. U of t dt is equal to integration from 0 to infinity e power minus st dt. Here 0 to infinity, u of t value is equal to 1, right? So 1 into e power minus st. Okay, from 0 to infinity, u of t value is 1. So 1 into e power minus st dt. Okay, so you integrate this, then you are going to get 1 by s. So Laplace of u of t is equal to 1 by s. Coming to unit impulse function, okay, represented by del of t. Del of t, okay, this is represented by del of t, unit impulse function. Okay, area of this function is equal to 1. Okay, area of this function is equal to 1. Okay, so simply Laplace of del of t is equal to integration from 0 minus to infinity del of t e power minus st dt. Okay, in place of f of t, you write del of t e power minus st dt is equal to, anyhow area of this is equal to 1. Area of this is equal to 1, and at t is equal to 0. Okay, this is defined at t is equal to 0, right? So you put t is equal to 0, then you're going to get 1. Okay, so Laplace of del of t is equal to 1. Okay, Laplace of u of t is equal to 1 by s. Laplace of del of t is equal to 1. Okay, coming to exponential function. Okay, e power minus alpha t. Okay, e power minus alpha t means exponentially decreasing, like this. If it is e power alpha t, exponentially increasing. This is what e power alpha t. This is e power minus alpha t. Okay, here actually this is the exponential function only, e power minus alpha t into u of t, okay, e power minus alpha t into u of t. Okay, it means this is defined only for positive values of time. For t greater than 0, this value must be equal to 1. Okay, this value will be equal to 1. Okay, so for t greater than 0, u of t value is equal to 1. Okay, for see, you can write like this: e power minus alpha t u of t, right? Okay, this is equal to e power minus alpha t for t greater than 0. This is equal to 0 for t less than 0. For t greater than 0, okay, this into 1. Okay, because u of t is equal to 1 for t greater than 0. Right? So Laplace of e power minus alpha t u of t is equal to integration from 0 minus to infinity. Anyhow, from 0 to infinity, this value is equal to 1. Okay, into 1. Okay, e power minus alpha t into 1 into e power minus st. Okay, because from 0 to infinity, u of t is equal to 1. Okay, so integration e power minus alpha t e power minus st dt. Okay, which is equal to, from this, I mean, after solving, you are going to get 1 by s plus alpha. 1 by s plus alpha. Okay, this operation is called frequency shifting operation. Sorry, frequency shifting operation, because in Laplace of u of t is what? Laplace of u of t is 1 by s, right? Laplace of e power minus alpha t u of t, okay, Laplace of u of t is 1 by s. In place of s, you write s plus alpha. Okay, in place of s, you write s plus alpha. Okay, you are shifting frequency. Okay, this is frequency shifting operation. Okay, so here see, Laplace of e power minus alpha t of t is equal to what? 1 by s plus alpha. Okay, yeah. This is what ramp function, e into u of t, ramp function. Okay, this is ramp function. Okay, this is what? T into u of t. Okay, you can write like this: t into u of t is equal to 0. Is equal to 0 for t less than 0, because u of t equal to 0 for t less than 0, which is equal to simply t into 1 for t greater than 0, because u of t is equal to 1 for t greater than 0. Okay, so meaning of this is including u of t to this function means t into u of t. Why you are including this? Because you can by including u of t in this function, you can say like this. This is defined for positive values of time. Okay, as this is defined for positive values of time, okay, this is included. Okay, including this means this function is defined for positive values of time. Okay, so Laplace of t u of t is equal to integration from 0 minus to infinity t into e power minus st. U of t is equal to 1 for t greater than 0. That is from 0 to infinity, this value is equal to 1. So t into 1 e power minus st dt is equal to 1 by s square. Okay, Laplace of t into u of t is equal to 1 by s square. Okay, if it is t into u of t means Laplace of t into u of t means 1 by s square, right? So Laplace of t into e power minus alpha t u of t means, okay, 1 by s square. In place of s square, in place of s, you write s plus alpha. If it is e power minus alpha t, you write s plus alpha. Okay, coming to properties of Laplace transform. Okay, first property is linearity property. Okay, linearity property. This is the given function. Okay, this is one function. This is another function. We are adding two functions in time domain means two functions. We can add two functions in S domain like this. Okay, a1 f1 of t plus a2 f2 of t means a1 f1 of s plus a2 f2 of s. Okay, this property is called linearity property. Okay, coming to scaling property, f of at is equal to 1 by f of s by a. Okay, time shift property, f of t minus a u of t minus a means e power minus as f of s. Laplace transform, this is this. Okay, e power minus at f of t, e power minus at f of t means f of s plus a, f of s plus a. Okay, this is what frequency shift. Okay, frequency shift operation, right? Okay, e power minus at f of t means f of s plus a, f of s plus a. Suppose f of t is u of t, then e power minus at, Laplace of e power minus at u of t is what? 1 by s plus a, s plus a, right? Okay, so f of s plus a, f of s plus a. Okay, next time differentiation. Time differentiation property. Okay, you are differentiating time domain function means in Laplace domain we are going to have formula like this: s f of s minus f of 0 minus. Okay, f of 0 minus is initial value. Okay, differentiating f of t is equal f of t in time domain means in Laplace domain could be, I mean, the function in Laplace domain or S domain could be f of s is equal to s f of s minus f of 0 minus. Sorry, f of t means in Laplace domain f of s. Okay, Laplace of d f of t by dt means s f of s minus f of 0 minus. Laplace of d square f by dt square means Laplace of this is s square f of s minus s f of 0 minus minus f dash first derivative of 0 minus. Okay, d cube f by dt square, Laplace of d cube f by dt square means s cube f of s minus s square f of 0 minus minus s f dash 0 of 0 minus minus f double dash of 0 minus. Okay, likewise you can also write for nth order differentiation. Nth order differentiation. Laplace of nth order differentiation. Okay, you can have this. Okay, next time differentiation. Okay, Laplace of this is this. Okay, frequency differentiation. Laplace of t into u of t. T into u of t means minus d by ds f of s. Okay, frequency integration, you know, right? Okay, next time periodicity. Okay, if you have any waveform, some time periodicity, okay, then you can have formula f1 of s by 1 minus e power minus st. Okay, t is time period. Okay, here, okay, fine. Next, coming to initial value. Okay, you can also find initial value. F of 0 is equal to limit s tends to infinity s f of s. So normally, in last unit, if you want to find initial value or final value, I mean, by using properties of inductor or capacitor, we will find initial value or final value, right? Okay, means if you want to find final value, at time tends to infinity, inductor acts as short circuit, capacitor acts as open circuit. By using those properties, of inductor and capacitor, you'll find I of infinity or v of infinity, right? Like that, right? Okay, so using S domain also you can find initial value and final values. Okay, so these are very important. These are very important. Okay, these of course these are also important. Okay, here initial value, finding initial value f of 0 is equal to limit s tends to infinity sf of s. Okay, finding final value. Okay, f of infinity, limit s tends to 0. See, this is frequency. S is equal to j omega. Okay, omega is 2 pi, right? Okay, so this is means f of 0 means t is equal to 0. The value at t is equal to 0. Here, the value at t tends to infinity. The value and time approaches infinity. Okay. Instead of saying t is equal to infinity, we can say like this: t approaches infinity or t tends to infinity. In practice, okay, we can find when t approaches infinity, right? Okay, so f of infinity means value. Okay, value of the function when time approaches. See, you take one example: e power minus alpha t. Okay, what is the initial value of this? Simply t is equal to 0, e power 0, then 1. Initial value is equal to 1. Okay, what is final value? That is 0. Okay, that's why you're going to have the waveform like this, right? Okay, final value is 0, initial value is equal to 1, right? Okay, so at t is equal to infinity, sorry, at t is equal to infinity, the value is what? 0. The value is 0 because e power minus alpha into infinity means the value would be 0. Okay, so f of 0 means if f of t is equal to e power minus alpha t, then f of 0 is e power 0 is equal to 1. F of infinity is e power minus infinity is equal to 0. Okay, so value of that function at t is equal to 0 is f of 0. Value of that function at t is equal to infinity is f of infinity. Okay, so by using S domain, okay, if we have f of s, okay, simply limit s into infinity s f of s is equal to, sorry, s f of s. Okay, then you can find initial value. Okay, by using this formula you can find final value. Okay. Convolution f1 of t convolution f2 of t is equal to f1 of s into f2 of s. Next here, see, Laplace transform pairs. Laplace of del of t is what? 1. Laplace of u of t is what? 1 by s. Laplace of e power minus at is what? Actually, in some textbooks it is written like this. Okay. Strictly speaking, it is e power minus at u of t. Strictly speaking, this is t into u of t. This is t power n into u of t. T into e power minus alpha t u of t. Okay. Okay. Generally, the Laplace of this is you can write. You can have Laplace of this 1 by s plus a. Laplace of t u of t or t 1 by s square. Laplace of t power n factorial by s power n plus n. Okay. Laplace of t into e power minus alpha t minus at is equal to 1 by s plus a whole square. Okay. Laplace of this is this, right? Laplace of s sin omega t u of t or sin omega t is omega s square omega by s square plus omega square. Laplace of cos omega t is what? S by s square plus omega square. Okay. Not required. These two are not required now. Okay. Laplace of e power minus at sin omega t is this is what? Frequency shifting operation. Frequency shifting operation. Okay. First you find Laplace of this is what? Laplace of this is omega by it is there, right? Omega by s square plus omega by s square plus omega square. Okay. E power alpha t means shifting operation. Okay. Frequency shifting operation. Okay. So in place of s you put s plus alpha, s plus a, s plus a. Okay. Here also cos omega t is s plus s by s square plus omega square, right? Okay. So e power minus at cos omega t means again frequency shifting operation. In place of s you put s plus a, then you get this s plus a by s plus a whole square plus omega square. Steps in applying the Laplace transform the circuit from the time domain to the S domain. Okay. Solve the circuit using node analysis, mesh analysis, or source transformation, superposition, or any circuit analysis technique which we with which we are familiar, right? Take the inverse Laplace of the solution and thus obtain the solution in the time domain. Okay, coming to circuit model. Okay, yeah. Resistance having the value of R. Okay, let V of t. V is voltage across R. V of t is the voltage across R. I of t is the current flowing through R. Okay, you know the voltage current relationship of the resistor is V is equal to IR. Okay, simply you write V is equal to IR, right? Okay, means this is in time domain. This is in time domain. Means strictly speaking, V of t is equal to I of t into R. Okay, this is in time domain. Representation in time domain. V of t is equal to R into I of t. This is in time domain. Coming to Laplace domain representation, taking the Laplace transform, okay, by taking Laplace transform, then we get V of s is equal to R into I of s. Okay, then this is in time domain. Okay, circuit element model in time domain. Okay, time domain representation. Okay, coming to S domain representation, instead of writing V of t across this resistance, you write V of s. You write V of s. Anyhow, R remains same. The current which is flowing through this is, instead of writing I of t, you write I of s. This is circuit element model in S domain representation. S domain. Okay, this is S domain representation. This is time domain representation. Okay. Coming to inductor. Okay. You know, right? V of t is equal to L di by dt. This is time domain representation. Time domain representation. Okay. So you know, right? Representation of an inductor in time domain. This is time domain representation. Time domain. T domain. Okay. V of t in time domain. I of t in time domain. there may be initial value. If it is charged inductor, there may be some initial value. Okay, L. Okay. Means this is in time domain. Time domain. Okay. In time domain, L is the inductance. In S domain, this will be SL. Okay, this is what impedance. Impedance Z of S is equal to what? Z of S is equal to what? You know, right? J omega L, right? JXL. JXL or J omega L, which is nothing but what? S into L only. S is nothing but J omega. S is nothing but J omega. Okay, this is time domain representation. Okay, so this is time domain representation. This is this is time domain representation. This is frequency domain representation. Frequency domain representation or S domain representation. Okay, in time domain it is L. In S domain it is SL. SL. Right. Voltage across inductor in time domain. Okay, let V of t is the voltage across inductor, I of t is the current flowing through this inductor. Okay, then what is the voltage across inductor in time domain? V of t is equal to L di by dt. Okay. V of t is equal to L di of t by dt. Right. By taking Laplace transform, taking the Laplace transform of the both sides gives what? V of t, Laplace of V of t is your V of s. V of s is equal to Laplace of you know, right, differentiating property. Okay, time differentiating property. Time differentiate, you have to use time differentiating property. Okay, L, this is constant. L into Laplace of, okay, you know, linearity property, right? Constant means constant doesn't change. So L, Laplace of di of t by dt means what? You know, right? Laplace of df by dt is what? Df of t by dt is what? Df is what? S f of s, S f of s minus f of 0 minus or not. Okay, S f of s minus f of 0 minus. Okay, so L into Laplace of di of t by dt is what? S I of s. Okay, because s into f of s. Okay, here f of t is what? I of t. S I of s minus I of 0 minus. Okay, because f of 0 minus, right? So which is equal to S L I of s minus L I of 0 minus. V of s is equal to S L I of s minus L into I of 0 minus. Here I of 0 minus is what? Initial value. If there is initial value, you must include that initial value in S domain also, right? So this is what? This is voltage across inductor in S domain. Okay, from this equation, you can find I of s, right? From this equation, you can find I of s. Then I of s is equal to 1 by SL into V of s plus I of 0 minus by s. Okay, from this equation, you have you got this equation, right? V of s is equal to SL I of s minus L I of 0 minus, right? Okay, from this equation, we can have I of s, which is equal to 1 by SL V of s plus I of 0 minus by s. Okay. We are going to get circuit models based on these two equations. Based on these two equations, we are going to get circuit models in S domain. In S domain with initial conditions. With initial conditions. So, what should I write? Okay. Let me use first equation. Based on first equation, how can I have circuit model? How can I have circuit model? Okay, what is the voltage? Anyhow, across element, voltage across element is what? V of S. V of S is the total voltage. V of S is the total voltage. Okay, which is equal to what? SL. Okay, what is the current? I of S. I of S is the current. Okay, so I of S is the current flowing through the element. Okay, I of S into what? SL. So you have inductance, impedance, SL. SL. Now it is I of S into SL. Okay, we are left with another part. Okay, that is minus L I of 0 minus. This is what? This is voltage only. Okay, V of S is voltage. S into SL into I of S is also voltage. SL is impedance. Impedance into current is voltage minus L I of 0 minus. This is also voltage. This is voltage. L I of 0 minus is voltage. Okay, so minus L I of 0 minus. So first terminal would be minus, second terminal would be plus. Then this is what? L I of 0 minus. Okay, if you put this plus minus, then you have to write it as minus L I of 0 minus. Now you check whether it is correct or not. V of S is equal to I of S into SL. I of S into SL plus voltage plus this voltage. Okay, so V of S is equal to SL into I of S minus L I of 0 minus. So this is the circuit model. This is the circuit model in S domain. This is the circuit model in S domain. Okay, based on voltage equation. Based on, now let us draw circuit model based on current equation. Based on current equation. Okay, so you're going to have parallel circuit. You're going to have parallel circuit because current will be dividing, right? Current will be dividing. So you're going to have parallel circuit like this. Okay, so let I of S is the total current. I of S is the total current. V of S is the applied voltage. V of S is applied voltage. V of S is the applied voltage, right? First part is what? 1 by SL V of S. 1 by SL V of S. Okay, so first you draw inductor. The current which is flowing through this inductor I1, you take I1 of S. You take I1 of S. Okay, I1 of S. I1 of S is equal to what? I1 of S is equal to V by S by impedance is equal to I1 of S or not? I1 of S, right? Okay, then V of S is the voltage across this element. I1 of S is the current flowing through this element. Okay, then V of S by impedance is equal to I1 of S. Then what will be that impedance? Impedance Z of S is equal to V of S by I1 of S. Okay, so V of S by I1 of S must be equal to what? Okay, V of S by I of S must be equal to what? SL. Okay, so this will be SL. This is what? Impedance of inductor. Okay, now we can check. I1 of S is equal to what? I1 of S is equal to voltage across this element V of S by impedance. Okay, so I1 of S is equal to V of S by what is the impedance? SL. Now you check whether it is correct or not. Okay, so it's correct. Okay, so you are done with one part. Coming to second part. Okay, second part is what? I of 0 minus is S. Okay, see, this is current, means this is also current as well as this is also current. Okay, so let me represent this part using current source. Okay, so This is what? I of 0 minus by s. Okay. So I of s is equal to I1 of s plus I of 0 minus by s. Okay. Here we have, right? Okay. Based on voltage equation, V of s is equal to I of s into SL plus L plus minus of L I of 0 minus. Okay, so I of s into SL, sorry, V of s is equal to I of s into SL minus L I of 0 minus based on voltage equation. Based on current equation, I of s is equal to the current which is flowing to this element plus current flowing to this. So what is the current flowing to this? Okay, V of s by SL. V of s by SL only, right? Okay, so V of s by SL plus I of 0 minus by s. I of 0 minus by s. Okay, downwards. Okay, because both are outgoing current. Both should be outgoing current because this is sum of these two currents. Okay, this current, the current which is flowing through. Okay, I hope it is clear. Coming to circuit model of capacitor. Circuit model of capacitor. Okay. Capacitor in time domain. Let V of t is the voltage across capacitor. I of t is the current flowing through the capacitor. Okay, let's see the capacitance of capacitor, right? We have the voltage current relationship of the capacitor. What? I of t is equal to C dV of t by dt, where V of t is the voltage across capacitor, I of t is the current flowing through the capacitor, right? This is what? This is the voltage current relationship of the capacitor. I of t is equal to C dV of t by dt in time domain. In time domain. Okay. Coming to S domain. V of t is the voltage across capacitor in time domain. Then V of s will be the voltage across capacitor in S domain. Okay. I of t is the current flowing through capacitor in time domain. Then I of s is the current flowing through capacitor in S domain. Okay. Now, what will be the impedance? Impedance is always the ratio of voltage to current. So, V of s to the ratio of V of s to I of s is what? Impedance. Okay, which is equal to what? V of s is, you can write I of s into 1 by Cs by I of s. Okay, so impedance is what? 1 by Cs. 1 by Cs. 1 by Cs. Okay. This is in time domain. V of t is voltage across capacitor. I of t is current flowing through the capacitor. C is the capacitance of the capacitor. This is in time domain. Coming to S domain or frequency domain. Okay, impedance of capacitor is what? 1 by Cs. 1 by Cs, right? So 1 by Cs. 1 by Cs. Okay. What is the voltage across capacitor? V of s. V of s is voltage across capacitor. I of s is current flowing to the capacitor. I of s is current flowing to the capacitor. This is the circuit model in S domain. In S domain. In S domain with zero initial conditions. Zero initial conditions. Zero initial conditions. Okay. With initial conditions, you're going to have let us have circuit model. Okay. Now, taking Laplace transform. Okay, you're going to get I of s is equal to what? You know, right? This is, you have to use time differentiation property. Laplace of time differentiation property. Okay, you know, right? L d f by dt is equal to f of s minus f of 0 minus f of 0 minus, right? Okay, so from this time differentiation property, we can write this: I of t is equal to c dv of t by dt, right? Okay, taking Laplace of this. Okay, I of s is equal to c is constant. Okay, linear property. C into Laplace of dv of t by dt is what? S v of s minus v of 0 minus. So finally, you're going to get voltage for current I of s is equal to S v of s, sorry, S C v of s minus C v of 0 minus, C v of 0 minus. Okay. From this equation, you can have voltage. Voltage is what? V of s is equal to 1 by SC I of s plus V of 0 minus by S. Okay. From this current equation in L domain, in S domain, okay, you can get voltage in S domain from this current equation. Okay. You know, this is given, right? I of s is equal to C S V of s minus C V of 0 minus. Okay. From this, we can get this voltage. Okay. V of s is equal to, you take this part, you take this to left side. Okay. This will become plus C V of 0 minus by SCS. That's it, right? Then you are going to get V of s. Now, this is the circuit model in time domain. Representation of capacitor in time domain. Okay, V of t is the voltage across capacitor, I of t is the current flowing through this, V of 0 is the initial condition. Okay, it is initially charged. Capacitor is initially charged, charge one. Okay, so now coming to S domain. Okay, let us take this voltage, current equation. Let me take current equation. Current is what? I of s is equal to ES into V of s minus C V of 0 minus C V of 0 minus, right? Okay, so current means we are going to have parallel path. So current will be dividing, right? So this will be capacitance, and we are going to have current source. We are going to have current source. Okay. Now the total current is I of s. Let I1 of s is current flowing through this. I1 of s is current flowing through this capacitor. Okay. V of s is voltage across this. Now, what will be this impedance? What is the first part? First part is, what is I1 of s? I1 of s is what? I1 of s is equal to C S V of s. Okay. This is I1 of s. C S V of s. From this, what is the ratio of V of s to I1 of s? V of s by I1 of s. V of s by I1 of s is equal to what? Is equal to 1 by CS. 1 by CS. So this would be 1 by CS. 1 by CS. Now coming to current. Current is what? Is current only. Minus C V of 0 minus. You do one thing. The arrow will be in upward direction. Then we can have C V of 0 minus. Then you apply KCL at this node. I of s is equal to I1 of s, means CS V of s, CS V of s minus CV of 0. Okay, this is the circuit model based on current equation. Based on voltage equation, voltage, what is the voltage equation? V of s is equal to I of s into I of s into 1 by CS, 1 by CS plus V of 0 minus by S, right? Then series connection. We are going to get series connection because we are going to have voltage equation V of S. V of S. Okay. I of S is current flowing to this element. I of S. So V of S is equal to what? First part is what? I of S into 1 by CS. So this will be 1 by CS plus this will be voltage. So plus. So plus minus V of 0 minus, right? So now V of S is equal to I of S into 1 by CS plus V of 0 minus by S. Okay, with 0 initial conditions, means V of 0 minus is equal to 0, I of 0 minus equal to 0. This is in time domain representation. Okay, circuit model of resistance in time domain, circuit model of resistor in S domain, circuit model of inductor in time domain, circuit model of inductor in S domain. V of S is equal to I of S into SL. Here V of S is equal to sorry V of S is equal to I of S. So it is written right. Okay. So V of S is equal to R into I of S in S domain. In case of resistor, in case of inductor, V of S is equal to I of S current into impedance. This is what J omega L, nothing but what? J omega is nothing but S. So SL into I of S. Okay, this is what 1 by J omega impedance of capacitor. So V of S is equal to current into 1 by SC. Okay, now you know, right? Impedance is the ratio, normally ratio of voltage to current. Okay, so Z of S, impedance in S domain is equal to, it is the ratio of voltage in S domain to current in S domain. Okay, three impedances. Z of S is equal to R, Z of S is equal to SL in case of inductor, in case of capacitor, Z of S is equal to 1 by SC. Okay, all are circuit models. Okay, with zero initial conditions. With zero initial conditions. You know, right? What is admittance? Admittance is the reciprocal of impedance. Now let us go through this problem. Fine. Find V naught of t assuming zero initial conditions. Zero initial condition. This is the given circuit in time domain. Okay, let us redraw the circuit in S domain. This will be the circuit in S domain. U of t. What is U of t in time domain? What is the Laplace of U of t? 1 by S. Okay, inductor 1 Henry is given. 1 Henry. What is the Laplace of this? SL. SL. S into 1, where L is equal to 1. So SL. So here, see. This is in time domain. Okay, this is the circuit model in S domain. SL. Okay, L means SL in S domain. So 1 Henry means, it is in time domain means SL is equal to H into 1. S. So 1 by 3, I think it is 3. 1 by 3, yeah. 1 by 3. C is given. C is equal to 1 by 3 farad. Then what is this? 1 by CS. 1 by CS, right? 1 by CS means 3 by S. 3 by S. This is in S domain. So U of t means 1 by S. Resistance doesn't change. R means in time domain it is R only. S domain it is R only. Okay, capacitance 1 by 3 farads means 3 by S. Resistance doesn't change. 5 ohm means in time domain it is 5 ohm. S domain also it is 5 domain, 5 ohm. Okay. Coming to this inductance, 1 Henry means L. This is L. L means SL. S into L. Here L value is equal to 1. So S, simply S. Now you apply KVL around this loop. Here you are asked to find V0 of T. V0 of T means voltage across inductor. So you apply KVL around this loop. Okay, minus 1 by S. Okay, otherwise 1 by S is equal to, otherwise you write minus 1 by S plus I1 of S into 1 plus 3 by S into I1 of S minus I2 of S. I1 of S minus I2 of S. From this you are going to have equation like this. Okay, you apply KVL around this loop, you are going to get this equation. Okay, similarly you apply KVL to this mesh 2, you are going to get this. Okay, KVL to this mesh means mesh 2. Let me write KVL to mesh 2. 3 by S into I2 of S minus I1 of S plus 5 I2 of S plus S into I2 of S or V0 of S. S into I2 of S is equal to 0. Okay, then you're going to get this equation. Okay, so solving these two equations, okay, you're going to get I2 is equal to 3 by SQ plus 8S square plus 18S. Okay, here I2 of S is this much, right? So here what is V0 of S? V0 of S is equal to I2 of S into impedance of this. Impedance is what? S into L, S into 1. So I2 of S into 1 S is what? V0 of S. So SI2 is V0 of S, which is equal to this is multiplied by S, then you are going to get 3 by S square plus 8S plus 18. Okay, then you know how to solve this, right? Okay. S plus 8 by 2. 3 by S square plus, okay, right, 3 by S plus 4 whole square. S plus 4 whole square. This S square plus 2 into 4 into S. Okay, 8S is okay. Plus 16, right? Okay, then we're going to get minus 16 plus 18 plus 18, right? Okay, it's same as this, right? You know, right? All these things. Okay, from this 3 by root 2 to root 2, because from this you are going to get 3 by S plus 4 whole square, okay, plus 2 means you can write root 2 whole square. Root 2 whole square. Root 2 whole square. Okay, see, it is multiplied by root 2 divided by root 2. Okay, then you can have this. Okay, root 2 by S plus 4 whole square plus root 2 square means omega by S square plus omega square. Omega by here this is frequency shifting. S by, sorry, omega by S square plus omega square means what? Sine root 2 t into e power, because frequency shifting, right? So e power minus 4t into root 2 e power minus 4t sine of root 2t poles, taking inverse Laplace. By applying inverse Laplace transform to this equation, we're going to get this. Okay, find V naught of t in a circuit, assuming V naught of 0 is 5 volts. Assuming V naught of 0 is 5 volts. Okay, initial value is given. Okay, so now in S domain, 10 into e power minus t u of t means, what is this voltage in S domain? 10 by S plus 1. 10 by S plus 1. Okay, resistance 10. Okay, coming to this, V of 0 is given means, you can have this, right? Capacitor in parallel with current source with initial value. Initial value is given means, this is what V naught of S. This circuit can be modeled like this. This is in time domain, this is in S domain. Okay, circuit model in S domain. This is what C V naught of 0. C V naught of 0, right? Which is equal to, what is the value of C? 0.1. 0.1 into what is V naught of 0? V naught of 0 is 5. It is given, right? 5 volts. Okay, then we are going to get 0.5 amps. Okay, this is what? This is 1 by CS. 1 by CS only, right? So 1 by, what is C? What is the value of C? Where it is? Yeah, where it is, yeah, it is given, right? C is equal to 0.1. 1 by 0.1 S means 10 by S. 10 by S. Okay. So you can have the circuit like this. You apply KCL at this node, then you are going to get this equation. 10 by S plus 1 minus V naught by 10 plus 2 plus 0.5. All are what? Incoming currents. Sorry. Yeah, incoming currents. These two are outgoing currents. V naught by 10, V naught by resistance, V naught by impedance. 10 by S is impedance of the capacitor. Okay. So after solving this equation, you're going to get this. After having partial fractions, you're going to get this equation. You apply inverse Laplace transform to this equation, then you're going to get V naught of t is equal to 10 into e power minus t. Okay, 10 into S plus 1 in Laplace domain means inverse, taking inverse Laplace of this is what? 10 into e power minus t into u of t. Okay, Laplace of this is, Laplace inverse of this is 10 into e power minus t into u of t. U of t plus Laplace of this is 15 e power minus 2t u of t. Okay. So this is okay. V naught, finally you're going to get V naught of t is equal to 10 into e power minus t plus 15 into e power minus 2t into u of t. This is okay. Either you write final equation like this, or this is nothing but V naught of t is equal to, you can also write like this, 10 e power minus t plus 15 e power minus 2t comma t greater than 0. T greater than 0. Either you write final equation like this, you can include u of t like this. No need to write comma t greater than 0. The meaning of this is, for t greater than 0, it is equal to 1. It is equal to 1 means this is the final expression. Okay, either you write like this. Okay, include u of t. Okay, no need to write comma t greater than 0. Okay, this is nothing but final expression, voltage across capacitor for t greater than 0. Okay, earlier we have solved first order differential equations and second order differential equations, right? Okay, finally we get expressions like this, right? Okay, in time domain, some equation. Okay, suppose you take series RL circuit. Okay, this can be solved. Okay, using differential equation, you can solve this equation. We have solved using differential equation. After solving this series RLC circuit, what is the current flowing to this? Finally, I of t is what? I of t is equal to V by R into 1 minus e power minus R by L into T. Am I right? Okay, this is for t greater than 0. T greater than 0. Okay, for t less than 0, it is 0. Okay, so it is for with 0 initial conditions, you have series RLC circuit, right? Okay, the response will be what? I of t is equal V by R into 1 minus e power minus R by L into T. For t greater than 0. Okay, either you write like this can be written like this: V by R into 1 minus e power minus R by L into T into U of T. Both are equal. Both are equal. Meaning of this is simply V by R into e power minus R by L into T for t greater than 0. For t greater than 0, it is equal to 1. Okay, both are equal. Okay, you can also use S domain. You can also solve RL circuit, series RL circuit, series RC circuit, series RLC circuit, parallel RLC circuit. Okay, all circuits can be solved using Laplace transform. Okay, is used to convert time domain into S domain. Okay, so first you take the given circuit, you redraw the circuit in S domain as it is given in time domain. You redraw the circuit in S domain. You use any one of the network techniques, KCL, KVL, source transformation, superposition, theorem, any network reduction technique. You use any network reduction techniques, okay, and solve. And finally, you use inverse Laplace transform to get the required equation in time domain. Okay, in time domain. Okay, see, if the input is given like this, if the input is some 10 into e power minus, you can see here it is given, right? 10 into e power minus u of t, it is difficult to solve using differential equation. Okay, so instead of using differential equation, finding particular integral, compute the solution. Okay, so instead of finding, I mean, using differential equation approach, okay, you can use Laplace transform approach, okay, so that you can get solution easily. Okay, finally this will be in time domain. Okay, you can use Laplace transform technique to this RL circuit. Okay, you solve this problem on your own. Okay, this homework. Here see 10 into, you know, right, 30 into e power minus 2t u of t. You know how to write this. Okay, initial value, is there any initial value? No initial value. Easy only. Okay, last and final problem. Okay, okay, we have two more problems. Okay, so t is equal to 0, current is given. Initial current is given through the inductor and 5 volts across capacitor. Any initial voltage? Yeah, initial voltage V of 0 is 5 volts. I of 0 is minus 1 amps. Okay, so Vs of t, Vs of t is 10 into u of t. In S domain, that would be 10 by S. Resistance doesn't change. Coming to inductor, this is inductor in time domain. Okay, in frequency domain, in S domain, you can read all the circuit like this. Okay, as it is having initial value, Ls is what? I of S by S. Okay. Okay. See, you can have circuit model based on voltage equation or current equation. Okay, you can also have series connection. Okay, series connection, right? You can also have parallel connection here. You can also have parallel connection here. Okay, instead of having series connection, you can also have parallel connection. So, as it is having initial value, okay, this is in S domain, right? you can rid of this element. You can have circuit model in S domain like this. 10 by already we have discussed about this, right? How can you get this? How we got this, right? So you apply case at this node. Okay, finally you're going to have the expression like this. Okay, okay. Finally you're going to have the expression like this. Using partial fractions, you're going to get v1 of s. Okay, applying inverse Laplace transform to the above equation, then you're going to get 35 e power minus t minus 30 e power minus 2t u of t, or this is nothing but what, 35 e power minus t minus 30 e power minus 2t for t greater than 0. This is also correct. Okay, writing this is meaning of this is for t greater than 0. So for t greater than 0, u of t is equal to 1. Okay, last and final problem. Okay, now assume that there is no initial energy stored in the circuit. Okay, I of 0 is 0, u of 0 is 0, t is equal to, right? No initial energy stored in the circuit, t is equal to 0. Means I of 0 is 0, v of 0 is 0. Okay, we don't have capacitance, right? So I of 0 is 0. I of 0 is I of 0 is 0. Fine. I of s is given 10 u of t. Is given 10 u of t. 10 u of t. Find v naught of s using Thevenin's theorem. Thevenin's theorem, we have to find v naught of s. Okay. Voltage across 5 ohm in S domain. We have to find. Apply initial and final value theorems to find v naught of 0 plus and v naught of infinity. Okay, let us find initial value and final value. Initial value and final values using initial value theorem and final value theorem. Using both theorems, you can find initial value. Using initial value, you can find initial value. Using final value theorem, you can find final value. Finally, you have to find using Thevenin's theorem, you can find v naught of 2. Okay. So first, let us find VTH. VTH. Okay, open circuit voltage, right? Where is the load? As you are going to find voltage across this 5 ohm resistor, this is the load. 5 ohm resistance is load. Okay, in order to find VTH, okay, VTH means open circuit voltage. Remove the load resistance. Okay, after removing load resistance, we can find VTH, right? So after removing load resistance, what will be the circuit? In S domain, what will be the circuit? Okay, after removing load resistance, this is what? 2ix. 2ix. 2i of s. Ix of s. This is in S domain, what is this? 10 by s. Okay, this is 5 ohms. Okay, in S domain, this is SL. SL into 2s. The voltage between these two is what? VTH or VOC. I have to remove the load resistance, right? So directly this current will be flowing through this. So voltage at this point with respect to this point is VTH. So VTH is equal to what? VTH is equal to simply plus 2ix plus 2ix plus 5 into 10 by s. 5 into 10 by s. Right? 5 into 10 by s. Now, you know, right, the current which is flowing to this is Ix. Ix is the current flowing to this branch. Anyhow, if you open the circuit, means if you remove load resistance, I of x would be 0 or not? Ix of x would be 0. Then this part becomes 0. Then finally you are going to get T by S. Finally you are going to get T by S. is what? It's VTH. Next, we have to find ZTH. Okay, so VTH, right? So I of x will be 0. Then this current will be flowing to this. Okay, anyhow, this will become 0. Then 5 into 10 by 50 by s. Let us find ZTH. The dependent sources present in this circuit, so he can't make all sources 0. He can't make dependent source 0, right? Okay, if all independent sources are present in the circuit, then by making all sources 0, you can find RTH between the terminals of the load resistance. Between the terminals of the load resistance, you can find RTH or ZTH. But here, dependent source is present. When dependent source is present, then how can you find ZTH? Using test cell or finding short circuit current. So VTH VOC by ISC or VTH by ISC is equal to what? ZTH. So already you got this value VTH. Let us find ISC. By short circuiting load resistance, you can find ISC. So short circuit load resistance ISC. You can find ISC. So IX is equal to ISC. So apply KCL at this node. After KCL at this node, then you are going to get minus 10 by s plus V1 minus 2x minus 0 by 5 plus V1 minus 0 by 2s. Okay. By KCL, you're going to get this equation, right? Okay. Here, Ix is the current flowing to this, as well as Is is the current flowing to this, right? Okay. So V1 is the node voltage, which is across each element. Okay. So voltage across this element is what? V1 only. Okay. V1 by Is equal to 2s. Otherwise, Is is equal to what? Is is equal to Ix is equal to what? V1 by 2s. V1 by 2s. Okay, by solving these two equations, you're going to get V1 is equal to 100 by 2s plus 3. 100 by 2s plus 3. Okay, right? The value of V1 means you can get the value of Ix, nothing but what? ISC. Okay, V1 by 2s. So, substituting this V1 in this equation, in the above equation, then you're going to get 50 by s into 2s plus 3. Okay, right? Already I've discussed. ZTH is equal to VTH by ISC. Okay, it is the ratio of VTH to ISC. VOC by ISC is equal to you substitute VOC and ISC in this, then you're going to get 50 by S by 50 by S into 2s plus 3. Finally, you're going to get ZTH is equal to 2s plus 3. 2s plus 3. Right? Next, VTH is how much? T by S. You can have Theorem equivalent circuit. ZTH is equal to 2s plus 3. Now you connect load resistance. 5 ohms. Right? 5 ohms. Voltage across this is V naught of S. Then either you apply KVL around this loop or you use voltage division rule, to find voltage across this. VTH, ZTH, 2s plus 3. Now we connect load resistance 5 ohms. Voltage across this is what? V naught of S. Okay. Here V naught is equal to VTH, total voltage, into that particular resistance pi by total impedance. Okay, you can use voltage division rule, or you can apply KVL on that too. Then finally you're going to get V naught as 125 by S into S plus 4. Okay, this is V naught. V naught of S. This is V naught of S. V naught of S, right? Now use initial value theorem in order to find initial value. So already you know the formula, right? V naught of 0 is equal to limit S tends to infinity S V naught of S. So limit S tends to infinity 125 into S. 125 into S by S into S plus 4. Okay, so both cancel. Okay. Then you're going to get 125 by S plus 4. Okay, then 125 by S, you can also write like this: 125 by S by 1 by 4. S into V naught of S, limit S tends to infinity, which is equal to S into limit S tends to infinity. Okay, S into 125 by S into S plus 4. S plus 4. So this is equal to, you can also write like this: 125 by S. Okay, correct. 1 plus 4 by S. When S is equal to infinity, means this part becomes 0. This part becomes 0. When S is equal to infinity means this part becomes 0. So 1 plus 0. 0 by 1 plus 0 is equal to 0. Okay. Anyhow, already in the question itself, it is given there is no initial value. Okay. So obviously, Q of 0 is equal to 0 only. Okay. So now next, coming to final value theorem, in order to know final value. Okay, final value, limit S tends V naught of infinity is equal to limit S tends to 0, S V naught of S, limit S tends to 0, 125 by S plus 4. Okay, so S is equal to 0 means, okay, S is equal to 0, then you are going to get 125 by 4, then you are going to get 31.5, 31.25 volts. So you are going to get final value. By partial fraction, already we got the value of V naught of S, 125 by S into S plus 4, using partial fraction. Okay, you can solve this. Okay, finally you're going to have V naught of S using partial fraction. Okay, taking inverse Laplace transform, you're going to get this equation. This is the final equation. Either you write the equation like this, otherwise 31.25 into 1 minus e power minus 4t for t greater than 0. This is also correct. In differential equation approach also, you can solve this circuit. It is easy to solve this type of circuit using Laplace.